All right, welcome to today's explainer. We are stepping straight into the arena, the Cambridge 0580 probability arena to be exact. Let's get real for a second. We are going to take raw data, past paper scenarios, and those complex math questions that usually make people sweat, and we're turning them into a clear-cut path to absolute mastery. Today, we're looking closely at how probability builds up from incredibly simple games to high-stakes, real-world crises.
But hey, before we start crunching the numbers, I want you to think about something called a false positive. You've probably heard the term, right? It's basically when you get a positive test result, but you aren't actually infected. Sounds like a simple testing glitch, maybe? Well, actually, it's a massive, real-world mathematical trap. It literally tricks human intuition every single day. We're going to unpack exactly how this happens in just a few minutes using some cold, hard data.
So, here is our game plan for today. We're hitting 4 main stages: the dice sum challenge, medical infection screening, Buffon's needle experiment, and finally, visualizing complex probability. Let's jump right in.
Okay, level 1, the dice sum challenge. We're starting off in some familiar territory here to build up those foundational skills.
Now, I want you to look at this specific Cambridge question and just think about it for a second. If you roll 2 standard 6-sided dice and add those scores together, what is the single most likely total? You probably have a gut feeling about this, right? But in the math arena, a gut feeling isn't enough. We need a rigorous visual model to actually prove it.
And here is that proof. If we map dice 1 right across the top and dice 2 down the side, we get this beautiful, complete sample space of 36 possible outcomes. Now check out that highlighted diagonal right down the middle. The number 7 appears exactly 6 times. It's literally the longest diagonal in the entire grid. There's no other number that shows up that frequently out of all 36 combinations. Seeing it laid out visually like this just completely takes the guesswork out of the probability, doesn't it?
Now, here is the brilliant part, and honestly, this is the algebraic leap you absolutely must make to secure those high grades. We're not just memorizing grid patterns here, we're generalizing the whole concept. Imagine stepping away from standard 6-sided dice. What if you have an abstract m-sided dice and an n-sided dice? Well, the total number of outcomes is simply m multiplied by n. Simple as that. Grasping this fundamental rule that your total sample space is just the product of the individual outcomes, that is your key to unlocking the really high-level questions.
All right, moving on up to level 2, medical infection screening.
Let's see how this all scales up from board games to real-world scenarios where, honestly, the stakes are so much higher. This is where probability jumps off the exam paper and becomes a massive issue of public health. Take a really close look at these 2 scenarios. We've got a population of 10,000 people. In Scenario 1, the disease infection rate is pretty high. It's 30%. But in Scenario 2, we're looking at a rare disease with only a 2% infection rate. Now, here's the kicker. Both populations are going to use a medical screening method that is exactly 95% accurate. You'd probably assume a positive test is equally reliable in both towns, right? Well, the contrast in the actual data is absolutely staggering.
So, where's the trap? It is hidden in those false positives we talked about earlier. Let's do the math on that 10,000-person town. In Scenario 1, with that 30% rate, 3,000 people are genuinely sick. Our 95% accurate test successfully catches 2,850 of them. Awesome. But it also hands a false positive to 5% of the 7,000 completely healthy people. That's 350 false positives. So out of 3,200 total positive tests, 350 are wrong. That's roughly an 11% false positive rate. Not terrible. But wait, look at Scenario 2, the 2% infection rate. Out of 10,000 people, only 200 are actually sick. The test accurately flags 190 of them. But that same 5% error rate on the 9,800 healthy people, that gives us 490 false positives. Let that sink in. You only have 190 true positives, but a whopping 490 false positives. By testing a huge population for a rare disease, the false positive ratio skyrockets to over 70%. It completely shatters human intuition. Crazy enough, if you test positive in Scenario 2, mathematically speaking, you're actually way more likely to be perfectly healthy.
Okay, let's step into level 3, Buffon's needle experiment.
Now we're escalating things. We're moving from applied models to a pure empirical experiment dreamed up by a French count. Probability, you see, isn't just formulas on a page, it's about observing reality. The count figured out that you could actually estimate mathematical constants simply by dropping objects. The steps are so elegantly simple. You measure a matchstick, drop parallel lines on a piece of paper exactly that same distance apart, drop the matches totally at random, and then just count how many matches end up crossing or touching a line. You are literally transforming the physical, random drop of a matchstick into hard, quantifiable data.
And this is exactly how Cambridge expects you to leverage your ICT skills and spreadsheets to track those results. Look at row 1. That tracks n, your total number of drops. Row 2 tracks little n, which is the number of matches that actually cross the lines. And row 3, that calculates your evolving empirical probability, little p, which is just n divided by n. As you drop that match 100 times, 500 times, 1,000 times, that probability dynamically updates right in front of you. It completely bridges the gap between a messy real-world physical experiment and a super clean digital model. Oh, and take a quick glance at row 4, calculating 2 divided by p. Keep that little formula tucked in the back of your mind for later.
Which brings us to our final challenge today. Level 4, Visualizing Complex Probability.
When exam data gets tangled up, you really need the right visual framework to decode it. You basically have two ultimate survival tools here: Venn diagrams and tree diagrams. Venn diagrams are your go-to for sets, unions, and intersections. Tree diagrams, on the other hand, handle sequential events, conditional probability, and mapping out a sample space over time. Knowing which tool to pull from your toolkit is literally the difference between getting totally lost in the numbers and securing a perfect score.
Here's the golden rule. Notice how simultaneous, overlapping categories practically scream for a Venn diagram. For example, if you have 120 students and some take physics, some take chemistry, and some take both at the exact same time, you need those overlapping circles to find that intersection. But if you're dealing with consecutive branch-like actions, like tossing a coin and then tossing it again, or reaching into a bag to pull out a counter without putting it back, that requires a tree diagram. You have to track how those probabilities multiply along the branches as time moves forward.
Let's put this into practice and apply that Venn diagram intersection logic to a specific student assessment problem. If the probability of a student having black hair is 0.7, brown eyes is 0.55, and the probability of having either is 0.85, what is the probability of them having both? Well, the probability of having either trait equals the probability of black hair plus brown eyes minus the probability of having both. Let's just plug those numbers right in. 0.85 equals 0.70 plus 0.55 minus our unknown intersection. Now 0.7 plus 0.55 gives us 1.25. So ask yourself, what do we need to subtract from 1.25 to get back down to 0.85? Exactly 0.4. So the probability of having both is 0.4. When you visualize that overlap, the algebra practically solves itself. As we wrap up today's explainer, I want to leave you with a really profound mathematical mystery from our source material, something to just kind of chew on. When you run Buffon's matchstick experiment thousands of times, that empirical probability starts to converge on a very specific, incredibly famous mathematical constant. So, what value does pi squared actually appear to get closer to as your drops approach 1,000? I'll give you a hint. Think about the shape of a circle, and think about the absolute power of probability to uncover the hidden geometry of our universe. I'll let you investigate that one on your own until our next explainer. Keep practicing, keep visualizing, and as always, stay curious.